This is section 11.1, probability. This is part 1, the nature of probability. In this section, we're going to learn how probability defines occurrences, how to calculate empirical probability, and how the law of large numbers applies to experiments. So probability is used in many areas, including public finance, medicine, insurance, elections, manufacturing, educational tests and measurements in genetics, weather, forecasting, investments, opinion polls, the natural sciences, and the game of chance. So, in a historical context, probability started from mathematical problems relating to games of chance and were studied by a number of mathematicians of the Renaissance. Below are a few of those mathematicians. Important ones were Pascal of France between 1623 and 1662, and obviously Jacob Bernoulli, which is 1654 through 1705. Pierre-Simon de Laplace was also extremely important in the 17th and 18th century. It's very important to notice, though, however, that in fact it wasn't until the 20th century that a lot of our ideas on probability started to take hold. So we start with several definitions. One is an experiment is a controlled operation that yields a set of results. The possible results of an experiment are called its outcomes. An event is a subcollection of the outcomes of an experiment. There are two types of probabilities that we're going to discuss in Part 1 and Part 2. Empirical probability is the observed probability of relative frequency of occurrences of an event and is determined by the actual observations of an experiment. Theoretical probability, which is what we would expect to see under a model, is determined through a study of the possible outcomes that can occur for a given experiment. Empirical probability, which we call sometimes relative frequency or observed probability, the empirical probability of an event, PE, can be determined by the following formula. PE of the event is the number of times the event has occurred divided by the total number of times the experiment has been performed. In our first example, in 100 tosses of a fair coin, 44 landed heads up. Determine the empirical probability of the coin landing heads up. The solution is, let E be the event that the coin lands heads up. So, for the probability of this event, it's 44 over 100, which equals 0.44. Using the empirical probability, Gregor Mendel developed the laws of heredity by crossbreeding different types of pure pea plants and observing the relative frequencies of the resulting offspring. These laws became the foundation for the study of genetics. For example, in the empirical study, he found that if you cross a pure yellow with a pure green, the first generation is yellow, not pure. In other words, it's yellow dominant and green recessive. Also, he found that if you have crossed a pure round with a pure wrinkled, you end up with a round dominant and a wrinkled recessive. Mendel called traits such as yellow color or round C dominant because they overcame or dominated the other trait. He labeled the green color and the wrinkled traits recessive. So now we go one step further. After first generation, we have yellow not pure, and if they crossbreed, they get yellow or green, is the second generation. And so also we have pure round, or round not pure. Crossbreeding with round not pure is round or wrinkled. So he found that approximately 3 yellow to every 1 green, and the second generation offspring approximately 3 rounds to every 1 wrinkle. As he continued his experiments, he found that the number of dominant traits for yellow seeds, 6,022, recessive trait, green seeds, and the number of recessive traits, 2001. So again, the ratio of dominant to recessive was 3 to 1 approximately, which was about 75% dominant trait. Round seeds, he found, with an experimental result of 5,474, and of those there was 1,850 wrinkled seeds. Again, it was close to 3 to 1 again, and again, the dominant trait was about 75%. Mendel concluded that the sex cells, now called gametes, of the pure yellow dominant pea plant carried some factor that caused the offspring to be yellow, and that the gametes of the green variety had a variant factor that introduced the development of green plants. In 1909, Danish geneticist W. Johansen called these factors genes. So the law of large numbers state that the probability statement applies in practice to a large number of trials, not to a single trial. It is a relative frequency over the long run that accurately predicts, not the individual events or precise totals. In other words, the law of large numbers says, as you conduct the experiment over and over again, your probabilities for the outcomes of the experiment start to approach the theoretical probabilities. Here's an example of tossing a fair coin. When we toss it 10 times, we see that in this experiment we got 4 observed heads out of 10, which is 40%. As we increased the number of tosses from 10 to 100,000, we see that we almost approach 0.5, which is our theoretical result. This concludes part 1 of our chapter on 11.1 on empirical probability or experimental probability. In the next part, we'll talk about theoretical probability, which is what we would expect to see under a probability model.